one energy goes up, the other goes down. What's the difference between these two graphs here? The one on the top is based on your time period, and the one at the bottom is based on displacement. Okay. Yeah. So when you have an oscillating system, you pull the oscillating system to the left, let's say, and as it raises height, it has maximum GP, but the K is 0 here. So you'll find that the GP is maximum and the K is 0. As you release it, it goes like that, and it crosses the equilibrium point. As it crosses the equilibrium point, all the GP is lost. So GP is 0, but it now has all K. So all the GP is lost, but K is maximum. And it just keeps doing it. So back and forth, back and forth. So GP to K to GP, GP to K to GP, right? So at any given point, if you add the two energies, you will get this line here, which represents the watt energy, the total energy, right? So the total energy of the system remains constant. We'll learn today, if time permits, that that is not true actually, because in reality, what happens to total energy as oscillations take place? It decreases, right? There's a term used for it. It's called damping. Damping is a process by which energy is lost to the surrounding due to energy loss over time. Okay, right. So this is the graph here, and this is another variant of it, like another take on it. So this was with time, like how time goes by and energy changes. This graph here is how energy changes with displacement. So my central displacement is 0, so that's 0. Anything that goes to this side is negative. Anything that goes to that side is positive. So negative যদি আসে, and I stop at this location, I have the maximum potential energy. Why is that so? Because the object is compressed here, right? But the K is 0. So maximum potential energy, but K is 0. As I release it, all the potential energy is lost, and it turns into Ke. So when it crosses the center, you have the greatest Ke, but no potential energy because the thing is not moving anymore. And then it goes the other way where the spring stretches once again, and it has maximum energy stored once again. So it's a graph that looks like this. Okay, that is the energy transfer for what? A mass spring system. Okay, with displacement. It would be the same for this graph as well. But what I'm trying to say is that the time graph for this and the displacement time graph for that are actually same. I've used two different examples to show them. It's not যে এইটার graph হচ্ছে খালি এটা, এই গ্রাফটাও কিন্তু এটা হবে। মানে any simple harmonic motion, time versus energy graph is this. Any simple harmonic motion, displacement versus energy graph is that. Okay, so it's not like it has to be only for this or only for that. Same graph. Only difference would be in that case, the graph would be little translated because it will not become 0. And the reason it doesn't become 0 is because there's always GP present. Okay. Right. So last class we also solved the question just to give you an idea. The Kiyashi chapter. So that was the question. It's very standard. The topic. So we are almost done. Electric field start karo, but we have two things left. I'm bolini ki ekta is called damping and resonance, and the other is a question. One single question that I'll provide you. Okay. So আমি যে গ্রাফগুলো provide করছি and everything else associated with it, right? It's provided on the next pages. You can just read through it. But I have one math for you. It's a math that's a test of your ability. So it apparently it means that you can solve any question from this chapter. Okay, let's try this. Okay, it's the most complicated you can get. So this is the threshold. Complicated even or a chapter to get. So they come apart in it. Okay. So it says that in a television game show, contestants have to pass under a barrier. So you have this barrier here. A barrier niche pass korte hobe. No, it's not there. Just you can take the answer. So this is the barrier here, and what's happening here is that the barrier has a vertical height, vertical height which is 0.7 meters, and it moves up and down with simple harmonic motion. खूब important, it moves up and down with simple harmonic motion. So this thing just goes up and down like that with a simple harmonic motion. What does that mean? Its velocity, acceleration, displacement graphs are all function of sine, cos, and they have what in it? Omega. Okay, so simple harmonic motion. Also, the acceleration is what to displacement here? Opposite direction and directly proportional. Okay, so that's what we know so far. State the condition that must be met for an object to move with simple harmonic motion. Very common question. Kiki, how are two things we just mentioned? That the acceleration must be what? Now, first the key. Acceleration is directly proportional. Acceleration is directly proportional to what? To displacement, correct. That's the first one. And what is the other requirement? The one you guys said? Yeah, and acceleration acts in opposite direction to displacement. Acceleration acts in opposite direction to displacement. Keep in mind that you could also just write the equation and narrate it, okay? Because that is the simple harmonic equation, A equals to minus omega square x, okay? So yeah, acceleration is directly proportional to displacement, and acceleration acts in the opposite direction of displacement. These are the requirements of simple harmonic motion. But look at this. This is the one I want you to solve, okay? 5 marks, you know. The bottom edge of the barrier is initially in contact with the ground. So bottom edge to ground edge to connected. And then it moves up to a height of 2.3 meters. It goes all the way up like that, 2.3 meters, before coming back to the starting position. So it's basically going up and down like that. Okay, so it's just going up and down continuously. It has a time period of how much? 4.5 seconds. So it goes up and down in 4.5 seconds. So it starts from here, goes up and comes back down 4.5 seconds. So it keeps doing that. Now, if you want to successfully pass under this, look at this statement. A contestant requires a space of how much? 0.6 meters to get under the barrier. So when the gap here is 0.6 meters, you can actually go under the barrier. You need to find out how much time does the contestant have so that the person can safely go underneath this. So it's just like, just continuously going up and down like that. And there's a brief moment here where the person can pass through. You need to find out the time that the person will be able to pass through. But what height do you need minimum to be able to pass through? 0.6 meter. So yeah, find the time in this oscillation that the object is how much higher from the ground? 0.6 meter. And since this is a simple harmonic motion, the equations of motion you do know. So I'm going to try karo. I want to see Parona theta. Typically, students do get it. Like there's always one or two students who get it right. Hello? 3 point. Like, main challenge is you need to get the equation right. Which equation do you have to use here? If you get that right, then the answer will be very straightforward. So spend more time on figuring out what the equation should be. Okay, after this. You could also draw a graph and imagine it a little easier with the program maybe. So you have to understand that this thing goes up to 0.6, right? And then from there till that point and back down is the time we're looking for. So it starts like this, it goes all the way up and then comes back down, right? So on the way up, it starts here at 0.6. Then it's above 0.6, above 0.6, above 0.6. It comes back to 0.6, then it stops. So you need to find that time, the time on the top. করে দিব forward. আচ্ছা, okay. দেখো কেমনে করতে হয়. So let me try to explain what's going on here. So you have this system where this object is going up and down like that, right? And একটা খুব important point mention করছে এখানে যেটার জন্য হচ্ছে answer অনেকের হয় না. It says that it starts from what location? So it's initially where? Yeah, contact with the ground. Okay, I'll zoom in here. So initially contact with the ground. So it starts from the lowest position there. So তোমার জিনিসটা হচ্ছে অসিলেট করার শুরুতে যেটা করবে, it's at the ground. তারপর গ্রাউন্ড থেকে কি করবে, এটা উপরে যাবে, তারপর নিচে এসে ব্যাক করবে, এরকম কিছু একটা, right? Now it's a simple harmonic motion. That means that the motion must follow what? Sine, cosine rule, right? Can you tell me if the object starts from the bottom, right? It goes like that, and then it makes its way up to the top and spins around. and then comes back to the bottom, right? And it comes back here. That's the motion that it should make, right? What type of graph does it generate? Yeah, it's not just a cosine graph, it's a negative cosine graph because there's an equilibrium point here. The biggest mistake that students do is they think that the original point is equilibrium. That's not true because it starts from the bottom, but it's actually going which way? Up. It crosses the center and then comes back down. আমাদের total height টা কত এখানে? The total height of this thing? Yeah, 3 meters নাকি হচ্ছে 2.3. So the object doesn't go all the way. So the height is 2.3 meters. So this is 2.3 meters. And what else do we have here? We have this height here, which is how much? Half of 2.3 কত আসে? Yeah, 1.15 is my initial displacement. So my initial object is how far from the center? 1.15 below, right? The total time taken for this oscillation is how much? 4.5 seconds. So I want to form an equation for this motion right now. Can you tell me what should the equation be? Eta ki sine na cosine? Yeah, so displacement equation is going to be, what was the general formula for displacement equation? Yeah, x naught cos omega t, right? So we need to make some correction here. Is my initial displacement going to be positive or negative? Negative, right? So minus 1.15 cos omega is going to be how much? 2 pi divided by 4.5 t. This is the equation for my displacement. Then you can start doing your question. Now, what displacement am I looking for when the object is how far from the bottom? 0.6 meter, right? Student are keyboard, they'll take 0.6 meter and do the math. This is actually incorrect. You can't do that, okay? The reason behind that is, are the displacement measured from the bottom to the center or center to the other sides? Again, in the equation, right? The displacement, is it based from the bottom or is it from the origin? Origin, right? Whenever you find an equation, right? Like let's say x naught cos omega t. In this equation, when you place your value and find a displacement, where is the displacement measured from? The origin, right? So এখান থেকে যদি আমি 0.6 meter এদিকে যাই, can you tell me from here how far should you be? I will repeat করতেছি. I need to be 0.6 meters from the bottom, right? But from the center, how far do you need to be? Yes, very good. Because this is going to be how much? This is going to be minus 1.15 and minus, so plus 0.6. This is minus 0.55 meter. So you need to find out the time at which the object reaches what distance? 0.55 minus 0.55. So the math korte hobe. So math kori amra. So my displacement is going to be minus 0.55 meters. And my original maximum displacement is minus 1.15 cos 2 pi divided by 4.5 t. Can you find the value for t here? 0.768 seconds. Okay. Achha, that's enough actually. Now let me explain what just happened. So the object started from here. The object started at this place and it's going up right now. It's going up right now. And then it crosses which line? The 0.6 meter height line, right? So at this particular location, like there, how much distance has this object covered from the ground? 0.6 meter. I need to find the time for which part? This upper part. How can I find the time for this upper part? If I know that the time taken to reach this point is how much? 0.768. Figure out what to. If the total time is 4.5 and the object goes from here to there, it takes 0.768. How much is that time there? How do we find that time on the top? Right, very good. So the time here is also going to be 0.768. When I'm talking about the interval here and the interval there, and 4.5 minus. Exactly. Okay, so therefore time above 0.6 meters is going to be 4.5 minus 0.768 into 2. Can you check how much is that? 2. 0.97. Gashular or 0.97? Yeah, that's the answer. Okay. So once more, let me explain to you what's taken it, the whole process from scratch. So you have this thing that's going up and down here, like up and down, right? We want to find the height it is above or we want to find the time when it's above what height? 0.6 meters. Unfortunately, whenever you model a simple harmonic motion, it's modeled around the origin. So even though you're 0.6 meters from the bottom, how far are you from the center? That's the distance we need to look for. So we know that this total height is 1.15, and we know that this part is 0.6. So that is the part that we need to find, right? So that's 0.55. So you do your math and find how much time will be needed for the object to reach that location. So it's how much? 0.67768, which would at the same time be there as well because it's symmetrical. So that's not the time we want, because these are times when the person can't actually go through it because the height is still not 0.6. The person can go through it during this duration where the height is above 0.6. So to find this time, what I do is I take the total time, and from the total time, I subtract this and that. So I'll get the rest of the time there, and that's the answer. Okay. No, so the object goes all the way to the top and then comes back in 2.3. So if you have an oscillation, right? Pendulum oscillation, right? So let's say you have a pendulum oscillation here, and the pendulum oscillates from here to there. What's the amplitude? Is this the amplitude, or is half the distance the amplitude? So I can repeat. If it starts from here, right, it goes that way and then comes back here. That's one oscillation. So think of like a cosine graph. It starts from maximum, goes to negative, comes back to maximum, right? So what should my amplitude be? Is amplitude half the distance traveled or a quarter? Quarter, right? Because let's say this is the zero line. Your object starts from here, goes there, goes to the bottom, goes up, goes back to the top. What is amplitude? Isn't it the maximum displacement from the rest position? So if my maximum up and down movement is 2.3, how far are you from the rest position? That is amplitude, right? So that's 1.15. Okay, so let's move on. It is just past paper, I think the most challenging one I found. So Pakigulo, I think, will be manageable. Last class we saw the variation of energy with time and energy with displacement. So when you have a simple harmonic motion, the object oscillates and energy transfer keeps taking place, like GP, KE, GP, KE. So in a pendulum system, what will happen is the object will continuously keep interchanging its energy. That's the word that we use. So it starts from GP to KE to GP to KE, back and forth like that. So if you plot a graph for GP, you'll see that the GP changes like that. And every time the GP goes down, what goes up? The KE, right? So once we plot the graphs here, we find that they're like completely mirror of each other because they're interchanging between themselves, right? However, we find that always, right, at any given point, if you add their values, they all add up to how much? That maximum value there. Okay, so that is the maximum energy. This is the graph with time. So when they ask with reference to time, this is how the graph looks like. Now with there's another version here, which is displacement, energy with displacement. So how does the graph vary with displacement? So as the object displaces left and right, how would the graph be? So as the object goes from this side to that side and back that side, the potential energy goes from maximum to zero to maximum. Okay, like that. So as the potential energy changes, the kinetic energy changes in reverse to it. So whenever it's at maximum potential, K is zero. Whenever it's maximum Ke, potential is zero. So it just keeps oscillating back and forth between those two. Okay, so it's basically displacement version here. So what you see here, both of these graphs are actually graphs for simple harmonic motion. One of them is with respect to time for energy. The other one is with respect to displacement for energy. Okay, so any simple harmonic motion out there, you don't know, let's say, what the system is. You know for sure its energy graph will look like that. Because a simple harmonic motion is always an interchange between two forms of energy. So it could be EP, KE, GP, KE, or it could be something else. If it's simple harmonic, graphs are always like that. Okay. Right, so let's move on. আমাদের আজকে we'll wrap up this chapter. So এটা হচ্ছে তিনটা গ্রাফ একসাথে করতে হবে। আমি আগে বুঝাই নি, তারপর তোমরা কপি করো। So page 82, go to page 82. 82 পাশে যে ব্ল্যাঙ্ক স্পেসটা ওইখানে আমরা লিখবো এটা। Okay, so দেখো, it's a very practical, realistic topic. মানে so far simple harmonic motion যা করছি ওটা realistic হয় না because of reasons. I'm going to show you what the reason is. This is number one reason. So if I go to a lab, right, and take a pendulum system here and make it oscillate, let's say like that. This is the oscillation that's taking place. You'll notice that the object keeps going back to the same place every time. There's no stop to it, right? It keeps going back to the same marker on the top. So there's no energy loss here. So the object is, look at the energy. So do you see the energy is continuously being interchanged between KE and potential energy? So the total energy is always the same, and you'll find that the blue and the green keeps swapping between each other, right? This is a unrealistic version. This is what theory would suggest, right? But in practice, there is definitely what acting on the system. Air, resistance, yes, drag, friction, right? What does that do to your system? It eats away energy from you. So, it's taking away energy. So how does that look like? So if I put friction here, I have a slider on the right. It says friction. See what it does. So do you see that over time, there's a red graph developing? That red graph is what energy? Thermal energy. That's due to work done against friction. That is due to work done against resistive forces. And you can see slowly but surely, your oscillation is now coming to what? Rest. This process, right, this effect, this phenomena is called damping. The correct term of this in physics is damping. What's damping? Damping is a process by which your system loses energy to what? The surrounding. Okay, so whenever you have an oscillating system and your object is losing energy to the surrounding, it's called damping. But there are different types of damping. What you're looking at right now, it's called undamped. Sorry, underdamped. Underdamped means this. Undamped was this. So I'll just go through one of them. This is called undamped. Undamped means what? There's no energy loss. It just keeps oscillating perpetually. There's no energy loss. If I give some friction out there, this is called underdamped. Underdamped মানে হচ্ছে damping হচ্ছে, but it's like not very instant. It's still taking time to stop, right? But then there's this one damping out there. I'm going to show you right now. See, okay? The oscillation will do this. That's it. আবার দেখাই. Do you see that? So it just stops instantly. I'll do that one more time. Do you see it just stops? This is also called damping. But this damping compared to the previous one is what? More intense, right? There's a name for this. This is called critical damping. Critical damping, you just shut it right away. You don't give it a chance to slowly, gradually lose energy over time. You just bring it to stop right away. Okay? So I'll show you like an experiment on this. It's one of the best experiments for our topic I have ever found. Okay, so oita korbo, but damping process, damping is a process by which your system loses energy to the surrounding, and it can happen very slowly, gradually. It can happen instantly as well. So what we need to learn first is the graph for it, and like a graphical chapter. So you need to know how the graphs for different damping. So let's say I have an oscillation going on here. This is displacement meter, and this is my time axis here. What does the damping look like if there is no damping? So there's a name for that process. It's called undamped. Undamped is a reference for both. So undamped is a scenario where the amplitude will remain what throughout? Same. No change, because you're not losing what to the surrounding? Energy. As a consequence of not losing energy to the surrounding, what does the system continue to do? Oscillate with the exact same energy, and everything is same, right? Yes, bolo. Thermal energy যদি হয় তাহলে damping. Oh, oscillations. Okay, it's oscillation, because damping is a systematic loss of energy in an oscillating system. Okay, so you have this scenario here. Do you get this? যে কি হচ্ছে গ্রাফটা নরমাল। So this is called undamped. Okay, নামগুলো খুব important. This is called undamped. This is very easy to remember because there is no energy loss or anything going on here. Undamped. Now, what does underdamping look like? Underdamping মানে হচ্ছে the yes, exactly. So you'll find that the amplitude is here. Now, এখানে একটা খুব interesting জিনিস আমরা দেখবো। You find that the amplitude is what over time? Decrease time. But can I just randomly decrease the amplitude, or is there a system to this? মানে আমরা কি এক্সামে বলবে sketch করতে? So can I just go down like that because I'm not no, I'm lazy. I don't want to draw many oscillation. I'll just go like শেষ। এই যে শেষ। Okay? Is that okay? No, why not? Yeah? Time period. আচ্ছা, time period point আসতেছি, but amplitude এভাবে কমানো যায় না. There's actually a system behind this. The system is, if you want to decrease the amplitude, and it's a quite advanced math here, the decrease in amplitude in an underdamped system obeys an exponential decay. I'll explain. Okay, it's like radioactive decay. So if I draw a line from the top of my graph here, do you see this amplitude graph here? So if I draw a line from the top here, and I, let's say, show an exponential decay. Do you know what the graph for radioactive decay look like? Like that, right? That's an exponential decay. It's the e to the power something function, or e to the power function to করোনা এখনো, but আমি দেখাই এরকম দেখতে হয়। করছো? এটা কি হবে তাহলে? minus e to the power x. So e to the power x is this, right? যেটা ম্যাথে থাকে। তো এটা হচ্ছে minus e to the power x, তো এটা হয়ে যাবে। Yes. আচ্ছা। So anyways, আমাদের ওইটা important না. The point I'm trying to make here is that it will follow a what function? An exponential decay function, which means তোমার যখন গ্রাফটা draw করবা, you have to draw like a line like that and follow the height of that. Do you see how this is like a gradual decay like that? Not like, straight down like that. That wouldn't work. It has to be a gradual decay. And I'll show you with math why is that so. Also, they'll ask you to prove that it's underdamped. How do you prove that? So I'm going to show you in a minute. So how do you prove that this is underdamping? So we need to do a bit of math, a math that you did in your O levels perhaps. It is called geometric progression. Geometric progression follow করে। I know it looks very random, but it's actually a very systematic decay going on here. So if I consider this height to be A, right? If I consider this height to be B, and if I do a ratio of A or B by A, tell me if you did this in math, it gave you something. What did it give you? R. Do you remember R? Like the fraction with which it keeps decreasing. Turns out that R value is what everywhere? Same. Which means if I find a C here, right? And if I do C by B, what should I get as well? R. And that is the proof that your system is undergoing what decay? An underdamped decay or an exponential decay. So whenever you get this question, they'll ask you to prove that it's undergoing a exponential decay or underdamped decay. What you do is you find these ratios. And I think 3 of them is enough. So tinta ratio বের করবে, and you'll show that the 3 ratios look what? Same. Which means it is not some random decay. It's actually following like a mathematical system. But why? Can it a mathematical system follow করবে? I'll show you with the math here. So the math is the equation for decay is this equation. We don't have this in our syllabus, but I think it's easy for you to understand. So equation for underdamping. So what is the equation for underdamping? It is going to be ওইটা না, আমি এই লাইনের ইকুয়েশন বলতেছি, এই লাইনের ইকুয়েশনটা। সো এইটার ইকুয়েশনটা হচ্ছে d equals to d naught e to the power minus bt. আচ্ছা, this is the equation. D equals to d naught e to the power minus bt, where b is called the damping coefficient. মানে তোমার different সিস্টেমের হচ্ছে different coefficient থাকে, air, water, right? So what's important for you, যেটা তোমাদের I think all level knowledge did enough. What is this e to the power minus bt going to be? D by d naught. Do you agree? Right. আমরা যে r বের করলাম is basically this. e to the power minus bt. E is a constant, d is a constant, t is a constant because same time period কাজ করা হচ্ছে. So therefore d by d naught always gives you a constant number. So that's the reason why all the ratios are okay. So তোমাদের যে this is where the equation comes from. So d is this and d naught is that. So d naught আর d ratio বের করলে and the e constant 2.7. So this is how what graph looks graph underdamped. Okay, underdamped is most of the scenarios in nature. Nature যে oscillations গুলো mostly underdamped. So underdamped মানে they'll gradually come to a stop. Okay, right, বলো আমাকে কোনো question থাকলে underdamping নিয়ে. Underdamping. The other one is undamped. নাম বলে একটু কাছাকাছি তো confusion হয়. Undamped means no damping. Underdamping means there is damping, but it is not very strong. But it's under, so it's very slow, right? Now let's draw on the same axis the graph for the other two. So the other ones, within the other ones, you have also axis taken here. Draw better. Nothing changes. It's just the same thing. Just I think visualize করতে easier my student there. Acha, coming back to what we're doing here, this is underdamped. Now, one very important thing, and this is like question of power for sure. During damping process, your time period doesn't change. So do you see how my amplitude is changing, but what is not changing? The time period. Be very careful. If your system is damped, right, it will still take what time to complete one oscillation? Same time. Okay, so always remember that damping won't impact your time period. And there's a reason behind this, which was removed from your syllabus 2017. রিজনটা হচ্ছে আমি একটা পেন্ডুলামের এক্সাম্পল দেখাই. পেন্ডুলামের টাইম পিরিয়ড অফ অসিলেশন এটা তোমরা এসে করে আসছো, মেবি ও লেভেলসে করে আসছো, মানে ইউ হ্যাভ সিন দ্য ফর্মুলা 2 pi root L by G. This is called the time period for oscillation of a pendulum. এটা কোথায় আসতো? এটা আসতো হচ্ছে তোমার ওই ও লেভেল ম্যাথে হচ্ছে কোন একটা ইকুয়েশন নাও বা কিছু করো, ওইখানে এটা আসতো. Homogeneous oscillation, right? So t equals to 2 pi root L by G. That's the equation. Now, if you look here, you'll find that time period depends on what? The length of your pendulum and the value of what? G. None of which change when a system is damped. So at the damped system, there is no energy loss taking place, obviously, but nothing is happening to your length. There's no change to the value of G. 2 pi is right? So there's no reason for T to change. So T will always be the same. Okay, so just remember that whenever you have an oscillating system, the time period doesn't change. Okay, Acha. Next comes the graphs that will make this chapter a little difficult to grasp for some students. But also critical damping, and there's something called heavy damping or over damping. Under damping, so over damping key, like word key mean correct. It's too much damping, right? How do the graphs look like? So graphs are a little strange. First graph is this one. এরকম দেখতে. So গ্রাফটা হচ্ছে হ্যাঁ. So this one is what you refer as over damping. আর আরেকটা গ্রাফ দেখাবো এখন. That will look very similar. That's why students get confused, which is this one. এই গ্রাফটা হচ্ছে ছোট হয় গ্রাফটা খুব. In that. These are the two graphs. Now, some students don't even get it. How are the oscillations? Because, do you see that it's just one line like that? It is actually an oscillation. The purple line that I've drawn here represents something that we call overdamping. Overdamping bola hoy. And the other one that we have here, this one is called critical damping. So what are these? Let me show you. So I'm going to video that বুঝানো যায়, and the video is like the best video for this topic, I feel. What দেখো তোমাকে এখন immediately stop হয়ে যায় না, ওইটা না. Like it's a very random experiment. ওরা যে এক্সপেরিমেন্টটা করছে ওটা কিন্তু এই চ্যাপ্টারের জন্য করে নাই. They just did it randomly, but it works very good for our chapter. I'll show you right now. So yeah, these are the different types of oscillations that we have out there. Okay, so for page so yeah, this one that you see here is your critical damping. This one that you see here is your heavy damping. Then the one you see here is your under damping. Do you see that the exponential envelope the graph that you are stuck between those two, right? And the other one is undamped. Okay, so all of them here together so that you can compare. একটা জিনিস true যে এই গ্রাফটা actually প্রথমে এখান থেকে নামে, so there's actually a bit of it before it. আমি বুঝাই জিনিসটা, মানে it has to go to a peak to fall, right? So peak এ নিয়ে যাওয়ার জন্য there's a bit of graph there, এরকম। So অনেক সময় দেখবা পাস পেপার আমি দেখি নাই, বাট বইতে দেওয়া থাকবে যে এটা এভাবে নামে, so sometimes students are confused. This is natural because they're supposed to do a normal oscillation, but then it stops suddenly. Normal oscillation এ কেমনে যাওয়ার কথা ছিল, এভাবে নাকি ulta দিকে, right? So it'll try to follow what the original graph was and then get damped. Same goes with critical as well. So the start of critical is actually going to be just like a normal oscillation, and then it suddenly becomes very drastically slow. Or check what I've seen in the mark scheme, there's no mention of it, but this is how the graph is supposed to look like. So yes, I will now show you and like a video that explains this thing, but oh, that's a good question. So which are intentionally access touch করতেও পারে, both of them are critical damping. So the thing is, access touch করা মানে কি, that the system will eventually come to the center, right? But critical damping doesn't come to the center sometimes. So that's why it's still considered critical damping. So imagine something is oscillating like that and you just hold it. It never came to the center, right? You just held it and you stopped it, right? It is actually a damping. What damping is that? Critical. Didn't make its way to the center. No, right? So that's why critical damping doesn't necessarily to come to the center. So they intentionally gap the raka so that you understand that it's not mandatory. What is mandatory for an oscillation to be complete? It stops. Yeah, stops. Where does it stop is not important. So in these, both the graphs I've drawn, the green and the purple, right? They stop. Okay, so they completely stop, but they don't stop at the origin, which is not a big problem for us. What's more important for us that they stop. So an oscillation is considered and deemed to be complete the moment it stops oscillating, not that it comes to rest. Okay, rest money origin. Okay, so let me show you that video. তাহলে অনেক কিছু clear হয়ে যাবে তোমাদের। এই চ্যাপ্টারটা অত পপুলার না in your like question paper. Oscillation পার্টটা আসে মাঝে মাঝে আসে না ওরকম, মানে it's not a shear short chapter. Shear short chapter গুলো তো হচ্ছে ওই যে gravitational electric fields, thermal physics for shear, right? So ওরকম কিছু চ্যাপ্টার আছে। No, electric fields, magnetic fields, that would be the core of our syllabus. তারপরে চারটা ছোট ছোট চ্যাপ্টার আছে, quantum physics, nuclear physics, medical physics, astrophysics. Yeah. So a example to that, এখানে sound level, let's check if there is sound. So this is an oscillation. এখানে একটা plate রাখা, scale রাখা, magnet রাখা, aluminum block রাখা, and সেটাকে oscillate করা হবে। Okay, the sound হয় নাকি? হ্যাঁ, আমি directly explain করতেছি। Soundটা খুব দরকার। Okay, so let me explain this experiment. What is this experiment? It's a chapter that we have later on. The experiment is not for this chapter. Well, it works good for me because it helps this chapter, but it's actually to do something called Lenz's law. There's a chapter in our A2 called Lenz's law. It's about how magnetic field lines have been cut, which induces an EMF and it produces a current. That current produces a magnetic field to oppose and slow you down. So এখানে magnet যখন oscillate করা হয়, and if you bring an aluminum block close to it, right, the magnetic field of the magnet is cut by the aluminum block. So in the aluminum block, what is induced? EMF, right? And because of the EMF, what starts to flow through that aluminum block? A current. And the current in that block will produce a magnetic field that slows your magnet down. and you find that the effect becomes more prominent the closer and closer you get. So দূরে থাকলে দেখবা oscillation অত impact করতেছে না, কাছে আসলে দেখবা it becomes more prominent. Also energy is lost. Lenz's law কিন্তু it's an energy conservation thing. The kinetic energy of your oscillation is lost as what energy in the material? Thermal, due to the current flowing through it. Okay, so anyways, see the animation. So sound is important. Okay, that's what damping. Sorry, কি damping ছিল এটা? Under damping. হ্যাঁ, undamped নাকি? Undamped হলে কিন্তু this would have gone forever, right? So পরেরটা যে আমরা okay, so সে কি করবে এখানে দেখো, I'll continue from there. সে ব্লকটাকে একটু কাছে নিয়ে আসবে। So এখন কিন্তু এফেক্টটা বেড়ে যাবে, the slowdown will be more. See what happens. Okay, so again oscillation holo, but this time what happened here? Yeah, it stopped a little faster, but it is still what damping, under damping, right? Because অনেকগুলো oscillation হচ্ছে না এখন, it's still under damping because it's still doing আচ্ছা আচ্ছা, ওইটা বুঝলাম, লেন্সেস ল, লেন্সেস লর জন্য। আচ্ছা আমি বলতেছি আবার। আচ্ছা, what do you think that was? Yeah, it's still under damp, but very heavily under damp. I know it sounds contradictory, but under damp because oscillation core low, right? But what happened? It came to stop after multiple oscillations, right? But that would be her next. This is very crucial, a part of the game. It's still under damp because they did multiple oscillation. Okay, however, don't worry. Yes, that's critical damping. Do you see it didn't do even one oscillation? It just came to a stop, right? আচ্ছা, তারপর দেখো বাকিগুলো। হ্যাঁ, না ওভার ড্যাম্পিংটা ডিফারেন্ট হবে, বুঝবা। But now was it shorter or longer than before? Over damping takes a lot of time to stop. Okay, so are over damp করা যাবে? হ্যাঁ, দুইটা জিনিস হচ্ছে, right? These are all over damping. Finally, this is the most over damped possible that we are. Thumbtaise, coming very close to stopping, and you see it's a very long time. So all of them together here. So the first four were under damped. That was critically damped, and rest of them are what? Over damped. See all of them together? Yeah, I don't think it's possible, but now focus for just yeah, so you can observe here, okay? See the critical damp and the over damp. Look at the time they take. Which one takes longer? Yeah, so the difference between critical damping and over damping. Now let's look at our graph here. You see the graph of critical damping and over damping are same, but what's the difference? Time. So over damping is a damping that takes the longest possible time to come to rest. Critical damping is a damping that takes the shortest time to come to rest. And under damped is the one that takes in between, and undamped never comes to rest. Okay, so তোমাদের question কি ছিল, অ্যালুমিনিয়ামটা কি করতেছে? So when that's a magnet, by the way, যেটা oscillate করতেছে, as the magnet is moving in front of the aluminum block, right? What does the aluminum block do to the magnetic field lines? আচ্ছা, so cut for it. So aluminum block is a magnetic field line, so it cuts the magnetic field lines, and because it cuts the magnetic field lines, there's the EMF induced. তোমাদের স্কুলে পরীক্ষা হয়ে গেছে। So EMF is induced, and because the EMF is induced, it's called Faraday's law of electromagnetic induction. So, okay, so because of Faraday's law of electromagnetic induction, what happens is EMF is induced, and because it's a metal, the EMF causes what to flow through that metal? A current. Yeah, and when there's current in anything, right, it produces a what around that thing? a magnetic field. Lenz's law states that magnetic field will always be such that it opposes your motion. So তুমি আসতে চাইলে এটা তোমাকে oppose করবে. That is what's slowing this thing down. Okay, and ওই শেষের দিকে হচ্ছে কেন এত heavy damp হয়ে যাচ্ছে, because not only Lenz's law is playing a role here, the magnet is in what with the aluminum contact. Because of that, what is also generated? Friction. So that's why it's getting over damped, like it's too much damping going on out there. Okay, so what are practical examples of this? Can anyone give me a practical example of an undamped scenario? Something that will oscillate perpetually forever. Hole create করে একজনকে ফেলাই দেবে এখানে, হ্যাঁ ঠিক আছে, okay, that's actually true. So that's actually true. So what you do is you dig a hole through the earth from one side to the other, you drop a mass, the mass will continue to go up and down like that, and that is perpetually oscillating. It well apparently no air resistance. But the better answer, or much more simpler answer, would be a mass spring system in space, or free fall, no air resistance. So gravity থাকতে হবে, otherwise oscillate করবে না. So yeah, that is one. Undamped খুবই rare. Can you give me an underdamped scenario? Yeah, just a pendulum that you do in your lab. That's underdamped. Okay. Now the ones that are interested, give me an example of an overdamped scenario. It is there. No, it's hard. Practically used. There are out there. Yes, very good. Car suspensions. Car suspension, it's actually like a spring, and the spring is designed to come to stop very slowly. Some of them are designed to come to stop very rapidly. Depends on what kind of comfort you want. So if you're in, let's say, do you know what a motocross is? Motocross হচ্ছে bike নিয়ে jump করে যেতে থাকে, or rally cars, right? ওগুলাতে critical damp করে কেন? Because if your car stops and lands, and then if it's like, doing that as it's going forward, it becomes very unstable, right? So what do you want? You want it to stop right away. They use critical damp suspension out there. They use over damped suspensions as well, but those are more comfortable. The car is pumping, you wouldn't know, but it's like slowly coming to a rest. You wouldn't realize it happening, right? So these are suspension systems. Race suspension, it's usually stiff, so critically damped. Yeah, because you don't want the car to wobble too much. And let's say comfort cars, sedans and roads, right? They have like over damping. You'll find the tires going up and down, or the car is floating on the top, right? So that's like that. What else? Another practical example of over damping. Bridges. Bridges damping করা হয়, but ওটা অন্য জিনিস করা হয়। ওটা হচ্ছে রেজোনেন্স বলে একটা জিনিস আছে, ওটাকে compensate করার জন্য. Yes, I was looking for that one. So you'll find that there are like doors in your home, sometimes in cupboards, that you release, দেখবা আস্তে করে এসে বন্ধ হয়ে যায়. Soft touch door বলে গাড়িতে, car doors, you'll see that they'll come like that slowly and then stop. And doors, like typical doors, they go উপরে একটা mechanism থাকে, like a thing with a lever out there. So দরজা কোনদিন জোরে বন্ধ হবে না, তুমি ধাক্কা দিলে it will just always slowly come to a rest and stop, right? That is over damping. Okay, because it takes a lot of time to come to a rest as well, বুঝছো, right? Good example. আরটা হচ্ছে pendulum নিয়ে আমি তিনটা বুঝাই, because sometimes students want to know that pendulum কে কেমনে আমরা চিন্তা করতে পারি. So undamped pendulum would be one that oscillates where? Space. Underdamped is one that oscillates where? Normally on earth, right? Overdamped pendulum is a pendulum that you release in honey. So there's honey, a bucket of honey, you release your pendulum, it'll fall slowly and then eventually and gradually finally come to a stop. It takes like water. So the thing is, that's called over damping. A critical damp is you release your pendulum and you stop it with a wooden block. So that's it, right? You just stopped it. That's critically damped. Okay. Over damping is like, it's gradually losing energy very, very slowly, right? So do you understand the concept? So yeah, these are called different types of damping. Next class we'll do something called resonance, and the chapter will be over. Also bring your test papers next class. I'll discuss that.